Hello, everybody, and welcome back to the final session for the afternoon. So we will now dive into Living Labs, and I'll pass things over to Sherif Zedan from Queensland University of Technology to kick off the session. Thank you.
Hello, everyone. My name is Sherif Zedan. I am the project manager for one of the Living Labs. Just share my screen. So this is just to show where the Living Lab fits within the iHub. So as you probably all know, there are the three activity streams. So the data clearinghouse IDS, which we saw in the last two sessions, and this is the Living Lab session. So the Living Lab actually involved a number of Living Labs that we use to test new technologies. So there are schools in ACT, HK in New South Wales, Children's Hospital in Queensland, and the Living Lab that I will be talking about today, which is the Fernhill Residential Aged Care. It's also in Queensland, in Sinkabucha. So the building is fairly new. I think it got occupied early 2021. And it involves a number of ESD features. So the ventilation is hybrid, so it combines between natural ventilation and mechanical ventilation. So the occupants, the residents of the rooms, they have the ability to actually open and close their windows. They have ceiling fans that they can control, and they also have control over the HVAC, so they can turn on or off the aircon. There are three chillers, so two of them are reversible. One is for cooling, and there's also BMS, which can be used to control the HVAC and lighting, and can also tell the building managers and maintenance people a lot of information about the building, about how to control it, and it raises alarms and alerts if there's anything that is behaving incorrectly. There's also a PV system of 100 kilowatt, and that can cover or that can generate around 144 megawatt per hour per year. Our Living Lab, we focused on 6 rooms, and then we also took into consideration the rooms above them and below them, so they have exactly the same layout, to be able to compare between the different performances of the technologies that we are testing. So we installed a range of sensors that can tell us the temperature, relative humidity, carbon dioxide, and motion. So a range of things, really. We also installed some reed switches that can tell us when the occupants open or close their windows, and then we can do further analysis on that. The technology, so we've tested a couple of technologies in that Living Lab. The technology that I'm going to focus on today is the honeycomb blinds. So honeycomb blinds is basically a type of blind that has a honeycomb shape, and that shape can trap air, which increases the resistance of that layer. So it basically adds a layer of R value to the window when it is closed. So there are different types of honeycomb blinds. They basically, the differences are basically in regards to their number of cells and the cell size. So we have tested 5 different types. So we had the single cell, different sizes, and then the double cell, different sizes as well. So the methodology, or just maybe I should mention that. So basically what we did, that we installed all these types. So we have the 5 different types. We installed them in the 6 rooms, as you can see, for all the windows and sliding doors in those rooms. So the methodology, in essence, there are 4 steps that are divided into 2 phases. So phase 1, the first thing we've done is that we basically calculated the performance of the honeycomb blind on site. And then based on the U value we got from that in situ analysis, we actually put that into simulation. and then we simulated the building. That we created a model for the whole building, and then we simulated that building with and without the blinds. Then the second step, or the second phase, we had interviews with the actual occupants who have been using the blinds to ask them a range of questions. And then based on their answers, we came up with operation scenarios that we again put into the simulation to show or to identify which scenarios work better, in essence. So this is the first step that we've done. So we have put some sensors to identify the heat flow through windows. So we put the heat flux sensor and the temperature out, temperature in, and then based on that formula, we managed to calculate the U value of the glass plus the blind. So in order to do that, we had, for each blind, we had to collect data for 3 days to comply with the standards for that procedure. And you can see here the difference between, so this is the external temperature, this is the internal temperature. To maintain or also to follow the standards, we needed to keep difference between the external and internal. So that's why we kept the internal temperature stable so that we can have more accurate results. The results of that process showed that the 5 types have different R values, and the reduction actually increases when the size and number of cells increase. So there is a correlation between number and size of the cell. So this is the blind with the lowest performance. So it only reduced 50%. Not only, that's actually a big reduction, but compared to the blinds that are double and 62, they can reach up to 62%. So you can see that the R value actually increases as we increase the number of cells and the size of the cells as well. So based on those numbers, we saw that we can reduce the U value by between 50 to 62%. So we've put that into simulation. So basically we simulated the windows of the building, of the whole building, with and without the blind to see the differences. So you can see here, this curve here showed the energy consumption throughout the year without the blinds, whereas that one showed the same consumption, but with the blinds. And you can see the effect of the blinds in reducing energy, especially in summer months. The same also happens when you compare between the cooling and heating. So you can see that major effect is in cooling actually compared to heating. So heating, we don't have that much effect. And that makes sense because the building is in a subtropical climate, so the winter is not that extreme anyways. This here shows the difference between with and without the blinds in terms of solar heat gain. So you can see the reduction in solar heat gain when the blinds are used, and also the heat transfer through windows. You can see also that reduction, especially during summer. This here shows the trends of energy consumption. When there's no blinds, you can see that the majority of energy consumption for that building is basically for cooling. So this is the heating and cooling combined. And the cooling, you can see that it's maybe more than twice the heating requirement. Simulation finding, we found that 38% of energy is for cooling when we don't use the blinds. When we use the blinds, we can reach 4.6% energy reduction in total and 12.5% cooling reduction as well when the blinds are being used. Then second phase, because basically all these analyses were based on that when the blinds are closed the whole time, but since that's not very realistic, so we went and we asked the actual occupants about how they use the blinds, so their operation schedules. We asked them for what are the reasons for them to open and close the blinds. And because all those blinds were actually motorized, so they had a remote control to operate. So we asked them whether that helped them or not. So in terms of operation schedule, we found that the majority actually keep the blinds open the whole day. Most of them, they close it at night. And Others, they just keep it open the whole time. In terms of reasons, we found also the majority, like not a lot of them actually operate the blind as response to external conditions. So like when it gets sunny or too hot, they basically use it in essence for security or privacy reasons. So most of them close it at night, for example, for security issues. In terms of motorized, so most of them said that having a remote control helped them use the blind more. However, the downside is that when they lose that remote, they can't find it, or the battery of the remote is depleted, they just like don't use it anymore. So because they don't know how to use it without remote. Based on that interview, we came up with 7 different scenarios in terms of operations. First scenario is when the blinds or drapes are always open, and then when the blinds are always closed. And then we also created a model for the normal curtain compared to the blinds. So we put the U value for normal curtains, and we simulated them when they are always closed. And then we created a scenario for when the blinds are closed only when the solar radiation incident on the blind is more than 120 watt per meter squared. We created a scenario when the blinds are closed only when the temperature outside is more than 24 degrees. And then we created a scenario when the blinds are closed at night and a day when the window exceeded 120. And then the last scenario when the blinds are open the whole day and closed only at night, because that was one of the scenarios that we found a lot of people do anyways. So this here shows the energy consumption for each scenario. You can see, of course, the majority or like the highest energy consumption is when the blinds are not being used at all. Followed by when the normal curtains are being used, but when it's only used when the solar incident is more than 120. The lowest consumption, of course, is when the honeycomb blind is always closed. And you can compare that, that's 24 hours closed honeycomb blinds compared to 24 hours closed normal curtains. And you can see the major reduction when the blinds are used in comparison to normal curtains. Then these 3 scenarios are basically, they reflect what are the common informed manner of operating the blind. So that's in response to like the energy, the external conditions. This here shows the effect of the different scenarios throughout the year. And again, you can see the effect is more effective during summer as well. This is the cost-effective analysis. Again, you can see that most savings in terms of energy bills happen during summer when the blinds are being used. So this is basically based on the differences when the blinds are used and not used. These are the savings you can reach. And in general, when we compared the honeycomb blinds to normal curtains, we found that the blinds can actually reduce energy costs by about 3.3% per year. We've also done analysis on the future weather. So basically what we're trying to find out is, will the blind be more helpful in the future with the global warming and climate change? So we found that the reduction is currently the blinds, if you didn't use the blinds, the reduction would be around 22.5. If you use the blinds, the reduction would be 22.7. So that doesn't really show that the blinds will have any additional benefits than what is providing right now to like reducing energy in the future. So to conclude, as I said, we had 2 phases. So phase 1, the in situ measurements, we found that U value is correlated with the size number of cells of the blinds. There are 50 to 62% reduction in the U value when the blinds are used. and there's an average of U value of 4.21 for the blinds only. The energy simulation of the blinds when they are closed and open the whole time found that for the energy simulation, found that 38% of energy is for cooling, 4.6% is the total energy reduction when the blinds are being used, and 12.5 is the total cooling energy reduction when the blinds are being used. And also the savings can reach up to $10,000 per year. Second phase, user experience, we found that most people just like they had an HVAC, they prefer to leave the blinds open. They rarely use it as a response to solar radiation because mainly they rely on air conditioning for heating and cooling. And then energy simulation of the different operation scenarios shows that 9% is the maximum energy reduction when the blinds are closed. 4% is additional savings when the blinds are compared to normal drapes. And the 6% reduction if the blinds are operated in an informed manner. So conclusion of all of this is that the blinds are effective as long as they are being used in an informed manner, used in the correct times. And that is why, because it is difficult to actually apply that in an aged care context, it's very difficult to get the occupants to use the blind in an informed manner. So that's why adding automated blinds or sensors that can respond automatically to external conditions can actually have a good impact on the reduction of energy through using the blinds. So that concludes the first part of the Living Lab, and now I'll hand over to Danielle and Michael to discuss their Living Lab as part of the work as part of the Uni of Wollongong. Thank you very much, everyone.
Thanks for that, Sherif. This has been a real team effort, this project, where we're looking at our Warrigal Shell Cove Living Laboratory, an aged care facility in Shell Harbour, Wollongong, where we've implemented a wholesale spot price service evaluation from a company called Flowpower. It basically lines up a lot with what Stephen White and Mehdi presented this morning on active demand response, the opportunities there. So I'll just tell a bit of a story about the pathway that we've been on to select these technologies to trial in this living laboratory, give a bit of an introduction to the demand response markets on the national electricity market, highlight how Flowpower, we see them as being a key enabler for predictive controls. Pardon me. And we'll share some results on demand response and ready to set up for phase 2 of our next trial following along from that. The Living Laboratory was opened in 2017, 128 residential care home beds, like you'd think of it as a nursing home in traditional terms, with 100 kilowatts of solar PV on the roof. Innovative VRF HVAC system, variable refrigerant flow, 258 kilowatts, which is demand response ready. The highlights from our baseline data analysis showed the plot here. You can see, if you can follow my cursor, the PV generation, typical daily profile. It's a 3-level facility, and we're just looking at the top level of residential care. The load profile for the top level, the HVAC load, was just fairly even, higher during the day compared during the night. And this is the total load with some peaks in the evening and the morning. Interestingly, just down the bottom here, you can see for winter and summer. So winter peaks are much more in the morning, summer peaks more so in the afternoon. The thermal comfort data, quite interesting as well. The highlights from that, just wanted to talk about the idea of energy flexible buildings. This is looking at the temperature time series data for 1 week in April, where if you look at the purple and yellow lines here, that's the common areas where during the day when it gets warmer, the HVAC kicks in to stop it going above 23 degrees. And overnight, again, the HVAC kicks in, interestingly, to stop it going below 19 degrees. So there's a fair bit of flexibility there, opportunity to adjust the temperature set point to time shift the loads. So it really shows that there is demand response opportunity in this living laboratory, but just wanted to point out that for an aged care facility, there's unique thermal comfort constraints and needs, obviously. So where there's a win for the electricity grid in time shifting loads away from these high usage areas on summer afternoons, that comes at the expense of thermal comfort for the aged, which we need to carefully consider, obviously. So we identified that there needs to be a win in this for the aged care sector, and a fun approach to look at this. I just thought, just playing on the rhyme on AEMO, let's take a bit of a swim through this big ocean of the national electricity market with Nemo and Merlin, his dad, who would say something like, the ocean's a big dangerous place with big players ready to eat you up. Stay safe, stay close. Don't adventure beyond our familiar area. And I must admit, I feel a bit like Dory as your guide in this marketplace walking through, but we've bumped into some of the wise, friendly turtles along the way to give us a bit of insight. So I'll just talk through this briefly, starting off with there's a number of markets on the national electricity market. Frequency control and ancillary services operate on the 5-second to 5-minute sort of range, managing the stability of the frequency, the grid frequency, and think about it like a car travelling along at a constant speed and in terms of the grid, that's 50 hertz to keep the grid going. When you approach a hill, like when the load increases on the grid, there needs to be a mechanism to provide more gas to keep the speed up. So that's that sort of market. At the other end of the spectrum, more on a seasonal sort of variation level, is the reliability and emergency reserve trader markets. They're set up so that when the grid reaches a situation where, if nothing is done, AEMO would need to start shutting down whole suburbs, blacking them out. So the RERT is set up to for major loads to shut down instead, or for major standby generators to kick in and provide emergency services there. They tend to last for 1 hour to 4 hours and there might be no events in a whole season, or there may be 4 or 5 in a season. So that was the opportunity we identified initially, but we quickly realised that there wasn't a lot of value in that just due to the short time periods overall and the high capacity for 4 hours. Next, we stepped up to a new mechanism, the wholesale demand response mechanism, which has just come into the market in October this year. The idea behind this is to enable demand-side customers, consumers, to participate actively in the spot price market. And as we started to look into that, we found that the trading limits were on a 5 megawatt sort of level. Sorry, I've just got a lawnmower going past. Sorry about that, the joys of working from home. And then, so with those limits, we found that we had a look at the wholesale spot price market and found that commercial and industrial customers can now participate directly on that market with some innovative service providers coming online in this way. This is just the front page of EMO, just showing an interesting example of how the states interact in the national electricity market. And this just shows a snapshot of a particular period when the spot price is actually negative in Victoria and South Australia due to large wind generation in Victoria and South Australia in such a way that generators actually have to pay to put electricity into the market during those periods, and consumers on the spot price market would actually get paid to use electricity for those times. So Flowpower, just getting onto them, they set up wholesale electricity agreements with commercial and residential customers where they expose their clients directly to the wholesale spot price. So the clients with predictive demand, active demand response can actually get increased benefits of those markets. Notice that they also provide a forecast for 24 to 48 hours to help predictive customers to actually utilise that. More recently, that previous slide was on a 30-minute market, but you can see now that these markets are trading at 5-minute intervals, so there's a lot more short-term fluctuations there. Just going on to results, we looked at 19 months, comparing a 19-month period from January 2020 through to July 2021, the data that we had available to compare the existing conventional fixed price contract that Warrigal's operating under compared with Flowpower's wholesale spot price for that same period. And interestingly, they came out neck and neck. When we look back at the data, we found here's the 19 months that we're looking at. And you can see that, beg your pardon, the 19 months is highlighted in red here. And you can see with the historic data from a few years before that, we just happened to pick out a very high spot price period, particularly towards the end of that period. But despite the fact that we picked out such a high spot price period, they were still neck and neck, even for a customer who was passive in their use of demand response control. So for 14 of the 19 months, wholesale price was substantially cheaper, and there are a few months that were higher. So when we look at December being a higher spot price month, 42% of the cost for that month of the energy cost for that month was in a 5.5 hour period when the price was above $500 per megawatt hour. And at the other end of the spectrum, if you switched off your electricity for half an hour or the HVAC system for half an hour, you would save 12% of the bill. So there's clear opportunity to, and I'll look at a specific example. That particular half hour that I mentioned is, you can see just in that period just here. So there's clear opportunity, and notice that this is the HVAC consumption on level 2. So during that period when the price is high, the demand, the consumption of HVAC at that time is quite high as well. But there's no reason, and these are the temperatures just going up and down, there's no reason why we couldn't shift some of this load beforehand and afterwards, just to reduce the load during those peak times. So there's short time durations for load flexing with a large impact on cost. The interesting thing about this is that HVAC and building systems have free inbuilt energy storage in terms of thermal mass with some temperature set point flexibility. Future plans, just to finish up. We see Flowpower as a key enabler with a suitable incentive for aged care HVAC demand flexibility. We're ready to move into phase 2 where we've engaged DNA Energy to do some active demand response in conjunction with Flowpower. And so we're looking very much forward to the results from this trial. So our Living Laboratories set up for green proving grounds into the future, where we've stepped the Living Laboratory through its paces and got some baseline data, and we're looking forward to trying the combined technologies in the near future, and going on from the end of this iHub project, looking for industry research linkage projects potentially. I'll just hand over to Dan now, who will talk through our school sector project.
Okay, thanks, Michael. Ever more to be known as Dory. So we're moving into quite a different space now. So Michael's talked us through the Warrigal Living Lab, and Sherif was talking about a similar healthcare living lab up in Queensland. The other sector that we're looking at in the living lab space is the education sector. So we've been working with ACT schools to establish a living lab to look at HVAC in the education sector. As for Michael's project, very much a team effort. So we've worked closely on both of these projects together. And yes, I'll walk you through our ACT Schools Living Lab very briefly and present the results of our first technology evaluation, which is a Hive transportable. So without giving too much detail, and I'm aware that we're probably a bit behind time, so I might fly through this all reasonably quickly. We've got two schools that we've instrumented as living labs in the ACT. So the first is AIRAH School, which is a relatively modern school. It's large, 1,800 students, constructed in 2004. It was constructed with passive design principles in mind, designed to operate without mechanical cooling in summer, although it does have air conditioning units being retrofit. It's a large school, so we had selected two sections of the school to be our living laboratory. The other school is Fadden, so it's very much a contrast. So I can probably help move this. It's very much a contrast to AIRAH. It's an older school, less energy performance in mind during the design. Yes, so in both cases, we've fitted out the schools with a sort of flexible evaluation or a monitoring system to allow flexible evaluation of a variety of different HVAC and renewable energy technologies and services. So in each case, we've got external weather station, internal temperature, relative humidity, CO2, energy consumption on a range of different sub-circuits with a focus on ensuring that we understand where energy is being used in terms of HVAC, so gas and hot water flows in some cases, and collecting BMS data where relevant, so for AIRAH. As I say, we set this up with flexibility in mind, so we didn't have specific technologies in mind to test. We're setting this up as a evaluation site for a range of technologies. I'm presenting today the first technology that we've evaluated, and we've got a number of other ones in the works. So today we're talking really about transportable classrooms or demountable classrooms. So they're a widely, ubiquitous feature of Australian schools. It's a solution to changing demographics and enrolment levels in schools. So the idea is that a transportable building comes in temporarily to provide space for a classroom while more classrooms are being built, or while there's a temporary bulge in the demographic curve, I guess. They're relatively low cost and consequently lower performance in terms of thermal performance and energy efficiency. But in practice, what we see is that transportable buildings often remain in place for a very long time and are used quite extensively. Of relevance to what we're talking about today, they're lightweight construction and typically all electric, so heating and cooling provided by a reverse cycle split system. This graph here showing temperature on the vertical axis in a cold week in September 2020 just shows the impacts of that lightweight construction. So you can see the purple and the red line here are one of the other more heavyweight buildings in AIRAH, and the yellow and the blue lines are the transportable buildings. And you can just see how much more closely the internal temperature follows the external temperature in these transportable buildings. So the technology that we were testing in this case was essentially a whole integrated transportable as a technology. So we weren't looking at a single feature retrofit to existing transportables. We were looking at this as an integrated technology. So the difference that Hive has between it and a normal transportable, it has improved insulation and air tightness, though still with low thermal mass. It's got an energy efficient air conditioning system. It has a solar array with battery storage, monitoring of the building and building energy usage and PV generation, and display so that students can use that in their learning, and smart control of temperature and ventilation. And I've bolded there insulation and air tightness and energy efficient electric AC because we were only looking at the thermal characteristics of the transportable in this study, and I'll introduce a sort of follow-up to this that is coming up. So thankfully, we had 2 transportables within our existing living lab. So there was, 3 transportables. So there was B13 and B14 in Amaru were transportable buildings, and Namaji Classroom at Fadden. So the Namaji Classroom was an older transportable. B13 and B14 from the outside look identical. We believe B13 was built in about 2004 and B14 was built in about 2010, but built by the same manufacturing company. And we also had a transportable, the Hive transportable was located at a 3rd site at Majura. So we had to install some additional monitoring equipment within the Hive building. Although it's worth noting that the Hive transportable was essentially already kitted out as a living lab. It already had temperature and humidity and energy consumption monitors, but we installed some of our own as a cross-check. So the aim of our test was to evaluate the overall thermal envelope and HVAC performance of the Hive transportable, and explicitly we were evaluating that in comparison to other transportables that we had within the Living Laboratory. Some of the key features of the buildings are laid out here. Of note, the thermal performance of the Hive transportable was more or less up to the current code. Well, I say more or less, it was up to the current code, but it wasn't a whole lot beyond the current code. So ceiling insulation was to meet Section J requirements, subfloor insulation to meet Section J requirements, slightly more wall insulation, and of note is double glazed windows, which are very much not a common feature of these buildings. The thermal envelope of the other 2 buildings, unfortunately, we were doing this testing during the COVID shutdowns, which meant that we couldn't get on site to do our normal investigation. So we were reliant on the ACT schools building service officers who were fantastic in getting us this detail, but meant that we couldn't do some of the things that we would have liked to do, like blower door testing or thermal camera surveys. Considering the air conditioning units, they were actually all pretty good in terms of their heating coefficient of performance. So the best unit was actually on the older Fadden Namaji Classroom. So it was a recently retrofitted air conditioning unit, but in general, they were all relatively energy efficient units. So we did a series of unoccupied building characterisation tests during the school closures, as I noticed. So the COVID closures caused a lot of headaches in terms of us not being able to be on site, and a lot of phone calls to BSOs trying to synchronise these tests. But the advantage of that was that we were able to directly compare these buildings. So as is typical in schools, each of these buildings had a different use case, and the occupancy would have been different, usage of air conditioning and window opening behaviour, that sort of thing. So in some ways, we were happy that we could put them through their paces while they were unoccupied. So we had 2 major tests. We had a startup period where we opened all the doors and windows to normalise the classrooms. Then we turned the air conditioning units on heating only mode for 10 days. At the end of that, we had another normalisation period where we opened doors and windows, and then we did a free running evaluation for 9 days. So just noting that there is a technical report that will be available shortly. So I'm going to fly through the results pretty quickly, but if you're interested, they'll be available shortly. So the active heating test, you can see just an example here for the Hive transportables. So we have the energy consumption for the air conditioning on the y-axis here, internal temperature on this y-axis, and the period of the test marked in red. So you can see that heating was started at this point, and we allowed 24 hours for the buildings to reach temperature and then run the test for 10 days from that point. So the interesting results, firstly, Hive transportables use less energy on an area and volumetric basis in comparison to AIRAH B14. But unfortunately, we can only make the comparison to one of the transportables because AIRAH B13 and Faden were unable to achieve the temperature that we asked of them. So in the case of Faden, one of the air conditioning units, which was newly installed, had a fault, which meant that it would turn off very shortly after we turned it on. That was fixed, but not until the end of the evaluation period. AIRAH B13, there was an issue with the thermostat. So for much of the period, it was controlling to 22 degrees rather than 25 degrees, despite us rechecking that. But there's definitely something else going on here as well, given that it's using twice as much energy as the other transportable classrooms to not achieve the temperature. And I'll talk about that a little bit more later. Moving on to the free running test. So this is after a period of normalisation where we opened the doors and windows for a school day and then shut them up again at the end of the day. What you can see here is internal temperature on the vertical axis and the period of the test on the horizontal. The red lines are the Hive transportables, the blue lines, the two AIRAH transportables, and the black line is the Faden transportable. So the Hive transportables are notably warmer throughout, overnight and during the day. And B13 is very notably a poor performer in terms of the free running test, in that it's almost exactly the same temperature as external. So the summary for the free running test: Hive transportables maintain the warmest and most stable temperatures compared to the other transportables. And as mentioned, B13 was a standout. So thermally, the only difference that was noted is that it has no underfloor insulation, but we suspect that there's substantial air leakages or potentially no ceiling insulation. But as I say, we're unable to get onto site during these tests to finally nut that out, but we'll be looking into that in the future. I should note we did check refrigerant charge and that there was no issues with the air conditioning unit, and that came back with a clean bill of health. So just quickly, as I mentioned, our test was really just looking at the thermal performance of the Hive transportables. They do also obviously have a renewable energy and battery system that is uncommon for these transportable buildings. We had a quick look at the performance during these tests, and the reason we didn't evaluate them on the basis of this is that our unoccupied tests were very much non-representative of school energy usage. But even when we were asking for 25 degrees, 24 hours a day, the RLUA, which is one of the two Hive transportables, was only getting 30% of the energy needed from the grid, and RLUB, which had a small battery storage, was getting 50% of the energy from the grid. So yes, fair opportunity for self-contained operation. We'll be looking into that more in the future. So just a quick summary: Hive transportables perform well in both active heating and free running tests. One thing that came out that's of a great deal of interest to us, and it relates to the earlier session about fault detection and diagnosis. So of the 5 buildings we looked at, 2 of them had issues with their split systems, one of which was a clear fault. The other one, it's still a little bit unclear what's going on, but in neither case had any fault been identified by the occupants, and it's unlikely that these would have been identified without the sub-monitoring that we were doing. And as I mentioned, we've got a follow-up evaluation looking at the interaction between the PV generation, battery storage and HVAC control of the Hive transportables, and notably looking at energy recovery ventilation, which is obviously a hot topic in terms of COVID safety. So I'm going to hand over to Wendy now to talk about the healthcare sector-wide work.
Okay, so as well as Living Labs themselves, what the Living Lab activity stream of iHub does has 2 sector-wide activities as well. So I'm going to speak about the healthcare sector Michael or Dan will talk about the school sector a little bit later. So the purpose of the healthcare sector-wide activities is to try to identify from the living lab performance and a few other activities what types of benefits can there be nationwide to the sector as a whole. So as part of the healthcare sector, we have established a knowledge sharing task group, and the people who have participated at the moment include health departments from Queensland, New South Wales and South Australia, a number of aged care providers. So in addition to sort of Bolton Clark and Warragul that are in the living labs, we have also engaged Baptist Care and Carinity. We have the private hospital sectors through Uniting Care and the Marta Group, representatives from Neighbours and a few private consultancies as well. And one of the tasks that the healthcare sector did was looking, we produced a report around August this year where we were wanting to align the health and energy co-benefits. The purpose of this was to try to, can we enhance the amount of energy efficiency and renewables in healthcare sector if we also identify co-benefits in terms of health? So we're looking at an integrated approach. It's one of the reasons, so what happens typically that a healthcare facility, whether it's a hospital or an aged care facility, for example, will typically have, around 50% or slightly more of its energy use is in space heating, ventilation and cooling. And the Neighbours tools at the moment, both Neighbours for hospitals, that's been around for a number of years, and Neighbours for aged care, which was only released a month or two ago, generally use energy use intensity as the key performance indicator. So it might be EUI, so kilowatt hours per square metre. The Neighbours tools also use somewhat a per bed day and are somewhat correlated by cooling degree days and heating degree days. But what the Neighbours tools and most of the energy KPIs around the world don't do is look at how is energy used within a whole of building or campus area. So one of the few pieces of information we were able to find comes from the US, where they were looking at the base load and peak load demand of different parts of a hospital, for example, comparing theatres, wards, imaging, laboratories, etc., to help facilities identify where are they using the energy the most and what the load factor of those particular areas are. So one of the first things we did for the report that we released in August was to first of all identify all the key literature in the last 5 to 10 years of what are the health benefits of looking after the indoor environment quality, so thermal, visual and acoustic comfort and indoor environment quality, indoor air quality. And so this is just a summary of one of the findings, for example. So indoor air quality practices in patient rooms in hospitals does rely on a few things that relate to the HVAC industry, so your microclimate and your ventilation strategies, but it also relies on a whole number of other things that could be put under, for example, integrated design studio things in terms of the location of patient rooms within the building itself, the room layout, anything about maintenance, cleaning, the users, and even policies of the company itself. From a ventilation purpose, also there are some interesting findings. We know that the objectives of ventilation are, provide fresh air to sort of maintain life of the occupants and dilute and exhaust pollutants, protect the building against moisture, etc., and contribute to thermal comfort. And typically the parameters that are used are your airflow rates, velocity distribution, your temperature relative humidity, and your filtration efficiency and pressure differences. But what I personally found interesting is that ventilation standards, and typically building managers will tell me, ASHRAE standards say that we must have, or the National Construction Code will say we must have a ventilation rate of X litres, etc. But the actual ventilation standards have varied over time in response to an understanding of and the relative importance placed on particular contaminants, on what the concentration limits of those contaminants are, and on different building types and on energy efficiency requirements. And there is no universal standard for what is the best ventilation rate or the best outdoor air rate, for example, because it really depends on what contaminant are you trying to control, how does it spread, what are your concentration limits, etc. And we found that in the last couple of years with COVID-19, for example. So the review of the literature on both all the building services and on the health impacts of those services just reveal that there are multiple complex interactions that take place. And those interactions, first of all, between the different user groups, so patients or residents and staff and visitors and their health needs, and then with building and health costs and the need to address greenhouse gas emissions, and then the need to look at changing climate. Pardon me. So if, for example, we're looking at what temperatures we use, use the set points for our buildings and how we humidify or dehumidify buildings has an impact on the energy use. Our ventilation and outdoor air requirements can improve or make worse the indoor air quality, but also impacts on energy and impacts on the thermal comfort. If we're trying to address indoor air quality from a contaminants point of view, and we want hard surfaces or surfaces that don't collect the dust or are harder to clean, that can then impact on whether those surfaces are sound absorbing and impact on acoustic comfort. Relying on openable windows for ventilation or windows for daylight penetration, etc., can affect visual comfort and acoustic comfort. So there are multiple interactions that aren't always considered when we look at just from a building services perspective or just from a health perspective. The other interesting thing we found in looking at, say, green rating tools, so whether it was LEED or Green Star, BREEAM, Minergie, etc., is that the allocation of points for indoor environment quality was typically somewhere around 15 to 20% of the total points, even though the achievement of good indoor environment quality has a really high energy perspective. So there seems to be a disconnect in the rating tools itself between the interactions between the environment quality and energy. And all of these things pointed to the need for good integrated design from the conception of a building or a major renovation and from a building operations point of view, and the need to integrate engineering, environment and health, and to have commissioning and monitoring processes that can report on all of those things. Another interesting finding was the different ways that health and engineering determine cost effectiveness. So typically in engineering and in building codes, for example, it's a cost benefit analysis, whereas in the pharmaceutical benefit scheme, for example, it's a cost value analysis, and they have quite different processes and inclusions and exclusions. The other area that we looked at relates to the International Energy Agency Annex 80, which is resilient cooling, and the need for healthcare buildings to look at what their resilience is to overheating and to power outages. So an interesting study on this came out of Germany that looked at the resilience of their total healthcare system. So everything from aging at home places to aged care facilities to minor and major hospitals, and found that while major hospitals were quite resilient to overheating and power outages, the further down the chain they went to at-home care services or aged care services that were much less resilient, and when a power outage or a heat wave emerged, that a lot of those places were not suitable for maintaining life preservation issues, and therefore hospitals became overwhelmed with the number of people that were seeking hospital services. So we're trying to look then at a vision of what an integrated health and energy system might be, and taking into account that there are both budgetary and energy resource constraints, that there are changing health delivery models, that hospitals are moving towards having shorter stays for patients. There's moves in a lot of countries for aged care to move towards ageing in place. We have climate change, we have resilience issues. But one thing that all of these things have in common is the emergence of sensors and systems to be able to monitor and measure these. So within the medical field, there's ambient assisted living systems, a lot of medical sensors, wireless sensors and networks, and software applications. So, for example, doctors can dial in to, if they're treating, we've had telehealth, but they can dial in and then see what are the ambient living temperatures in the patient's home, for example, and might that be exacerbating the symptoms of the patient. We have a whole emerging range of cheaper indoor environment quality sensor systems for your thermal conditions, air quality, etc. We're having smart energy management systems for the control of devices, for PVs, for battery charging, demand management, etc. And we have the ability now to be able to have building management control systems, some of which were talked about in the DCH session earlier today, that can be event-driven and distributed control. So out of all of this, our report was sort of recommending that in terms of key performance indicators, we need much more nuanced KPIs than the energy use intensity, and we need it at different levels. So we're suggesting that we need whole of building or site KPIs that look at energy use. So we typically do this already. Greenhouse gas emissions, we typically do. We don't necessarily in Australia have KPIs that report on what the network impact is, what the load flexibility is, the demand response capacity, or even what the progress is of a particular site towards net zero carbon. But in addition to that, we also need much more nuanced KPIs relating to energy use and metrics within a building services level. So what are the thermal comfort metrics? What are the acoustic comfort metrics? The lighting, indoor quality, air quality metrics, for example. We need resilience metrics that account for the risks of overheating and power outages. And this is some of the work that's happening in the Annex 80 work in looking at what these resilience metrics might be. And then also health metrics that can be used to quantify and qualify the additional value that can result in energy-focused actions. So, for example, if you improve the lighting comfort, if you improve lighting by putting in LEDs and programmable LEDs from a lighting colour rendition point of view, and it costs X amount of dollars, but you can also show that by changing the colour of the lighting and by making the lighting mimic the varying intensity of light over a day-night cycle, for example, that the benefits of that in terms of elderly people's sleep cycles and agitation of dementia patients can have some healthcare benefits in terms of staffing and medication, for example. So the next steps of the healthcare sector-wide and what our deliverable is by May next year is a renewable energy roadmap for healthcare. And in that sense, moving into the next section of looking at what the next tasks are. So the Healthcare Knowledge Sharing Task Group met in July, where we sort of met each other and looked at what are the standard KPIs that each of the sectors were using and what do neighbours use and what are our interests, the various members' interests and alignments. And the goal of this group is to help in the development of the renewable energy roadmap. We're disseminating some of this information that I've just presented to you now. We're presenting to the healthcare sector broader in a forum that's being held in Brisbane next week. So there's an organisation called Global Green and Healthy Hospitals and a Climate Health Alliance are having their annual forum in Brisbane. So we'll be presenting some of this information to them. And then the following week, meeting with our task sharing group to workshop on a rough outline or framework that we have for the roadmap. Then over December to March, we'll work on a draft roadmap that the knowledge sharing group will then look at in March to review, and so we can finalise for reporting then in May. Then we have a potential future project that's going through the AIRAH approval stage at this moment, just waiting for ARENA funding. So this new project is focused particularly on net zero energy and resilient hospitals, and the project partner, if approved, will be the Australian Health Infrastructure Alliance. So this is the alliance of all Australian state and territory public hospital departments and New Zealand public hospital departments. And we're looking at a desktop study of 4 working packages, in essence looking at the impact of future climates on hospital energy and demand. And that's because the Health Infrastructure Alliance are the keepers of the design guidelines for hospital facilities. So can we inform how those design guidelines might have to change in order to meet so that the building envelopes are suitable for future climates? We want to model the impact of HVAC operation due to COVID. So, for example, the Victorian Health Department has put out suggestions on what the different ventilation strategies should be in order to reduce COVID spread in hospitals. We want to, but the hospitals don't know what are the kilowatt hour and kilowatt impacts of those suggested changes. Looking forward to modelling the impact of different climates and HVAC operation on net zero energy, and looking at the potential participation of healthcare facilities on the energy market through demand response or FCAS, etc. The timeframe for that work, if approved, would be February to May 2022. So I think now Daniel and or Michael are going to present what the future work or the additional work for the schools sector is.
Thanks for that, Wendy. That's very similar to what we've done in the schools in a lot of cases. I think the relationship between HVAC and learning environment quality and things like that is we've looked at that in our baseline education sector-wide report, and I presented on that in the previous iHub webinar. So I just wanted to very briefly talk about the future work that we've got planned for the education sector-wide report. So we have gone out to each of the state education departments and asked them to share what data they have available about the energy consumption of their schools. And we've managed to compile a pretty substantial data set of energy consumption in schools across the country. So we've got, for Victoria and the ACT, we've got 15-minute interval data. In the case of the ACT, we have solar generation and separately consumption. For Victoria, we just have net metered data. For New South Wales and Tasmania, we have monthly billing data, and for Queensland, we have annual data. And that's for various time periods for the different regions, but we have some common years that we'll be looking at. And we did try and get data for South Australia, Western Australia, and Northern Territory, but for various reasons we weren't able to. And the reasons that we weren't able to are, in some cases, just as interesting as looking at the data itself. So it just gives us an opportunity with this data to do some interesting things. So, for example, looking at the impact of climate zone on school energy consumption, the impact of, is it more appropriate to have students per kilowatt hours per student or kilowatt hours per metre squared as a normalisation factor for schools? This is just showing number of students per versus gross floor area for schools, and obviously there's a close relationship between those two things. So really, this is just a note to watch this space. We'll be presenting the results of this analysis at upcoming events, but we'll first present them back to the education departments who've supplied the data before we share any results at the state level. So that's all I've got to say about the future work for the education sector wide.
Great, thanks very much, Dan. Are there any questions? There are no questions in the Q&A session, and we're just about out of time anyway. So I just want to let all participants know that, you know, feel free to contact anyone here at QUT or Uni of Wollongong if you have any questions about any of the information we've presented today, or if you have a technology that you think you might want to test at one of the living labs. Even though the iHub money for testing has in essence been fully allocated, I think the intent is to try to keep the living labs going for a while, so there may be opportunities for doing some testing down the track. So Dan or Michael or Sherif, do you have any key findings or messages you want to leave with our audience today?
I mean, I think the key message from me is that we have the technology reports are going through the review process, the iHub review process at the moment, and they'll be published on the iHub website. So, I mean, from our perspective, we've given a very high-level overview of the work that we've done, but if there's interest, then all the detail will be in the technology reports.
I think for me, in listening to both the IDS and the DCH sessions earlier today is just how much overlap there is between all three, and they're not three clearly delineated activity streams. And I see that some of our living labs and the healthcare sector, for example, would really benefit from having a DCH approach and a asset portfolio approach to managing some of their things. Sherif, was there something you want, or Michael, did you want to add anything?
I guess one thing maybe I want to add about the honeycomb blinds is the idea of actually testing the automation of the blinds. If we have the opportunity, time, or money to actually implement sensors and do that, that might actually have will give us a good understanding about how we can increase the potential of the honeycomb blinds. But that is something I suppose we can maybe do as a future type of project, whether it's at the living lab or a different living lab. And the other thing is the potential of honeycomb blinds to be also part of the analysis that we do for the NCC, because I had that conversations with some of the suppliers. And I suppose if the whole thing is automated, there might be a chance, or like there could be a way to put some credits for people who are using shading or like window dressing in terms of reducing energy then for buildings in Section J.
And for me, one of the advantages of looking at internal window dressings is that it can be a relatively cheap but effective retrofit for existing buildings without going into, because a lot of Queensland buildings, or a lot of Australian buildings, are still single glazed without, sufficient insulation and shading, etc. So looking at cheap retrofit options or easy retrofit options for older buildings is also a benefit of this. So if there's no other questions, I think we're right on time anyway, and we probably all need to get up and stretch our legs a little bit. So thanks everybody for participating, and keep an eye out for all these technology reports that will be coming out on the iHub website in due course as they've gone through the vetting process. So thanks everybody for participating, and good afternoon.
Thanks, Wendy. Yeah, so just to wrap up things there, everybody. So that does bring us to a close for today's Knowledge Summit. Special thanks to everybody who registered and attended today's session, and special thanks to all our presenters as well. For any information on iHub or to watch any of the past recordings of the summits, please hop onto the iHub website for more information. So thank you all again. I do hope everyone did enjoy today's session, and we look forward to you joining us next time again soon. So thank you, everybody.